This is AP Calculus AB, and we are focusing on the second derivative test. Well, the second derivative is primarily used to determine intervals of concavity and points of inflection. It can also be used to identify relative maximums and minimums of a function. So this is the second derivative test. It's to identify relative extrema, which are minimums and maximums. You can use the second derivative test in two cases. One, if the first derivative is equal to 0 at a specific a value, that means that a is a critical value. So that's one scenario. If f prime of a is 0 and the second derivative of that same critical value is positive. If that happens, you're going to have a relative minimum at that x value. If the first derivative at a critical value is equal to 0, once again, and the second derivative at that same x value, the same critical value, is negative, less than 0, you're going to have a relative maximum at that x value. So looking at this graph, let's just discuss this for a moment. I think that we would agree that this part of the graph is concave up, this part of the graph is concave up, and the blue part of the graph here is concave down. As far as f prime being equal to 0, which is what this is saying, if we draw a tangent line at A, or at B, or at C, I think that we would agree in each of those scenarios that the derivative, the slope, is 0. Right now I'm just trying to make the case for this second derivative test to make some sense to you. So in these three situations, the first derivative is equal to 0 as a horizontal tangent line. Now it claims that when the second derivative is positive, you're going to have relative minimum. So we're saying that here and here we have relative minimums. But how can we know by looking at this, how does it make sense that the second derivative is going to be bigger than 0? Here's how it makes sense. If you examine the slopes from left to right as we continue down through here, let's say each of these little segments represents a tangent line. Let's say the slope here, let's say is -3. This one's not as extreme. Let's say it's -2. Then it's 0 here. Now let's say over here we are at 2 again. And here, let's say that we're back to 3. How are the slopes changing? How are the derivatives changing? Well, they're getting bigger. The numbers are increasing. So if the first derivative is increasing, they're getting bigger. That means that the second derivative, which is measuring how the first derivative is changing, that's saying that it's positive. So we are saying here that if the second derivative is positive, that means that our graph is concave up. And if our graph is concave up, that means we're going to have a relative minimum. Side note, my cat ignores me all the time. All the time. Never gives me any attention, but right now when I'm trying to make this video, she won't leave me alone. She's pawing at me. She's sitting on my iPad. Cats are real jerks, I'll tell you that. Sorry. Looking at the blue part of the curve, we can see that these slopes here, positive, it's pretty extreme. You know, like maybe this is 2, and then we got 0 here, and then here it becomes negative. Let's say -1. Looking at those slopes, it's going to 2 to 0 to -1. So the first derivative, the numbers are getting smaller. That means the second derivative is negative. When the second derivative is less than 0, that part of the graph is going to be concave down. And when the graph is concave down, it's going to be a relative maximum. So we'll do an example here, but just want to point out when you can't use a second derivative test, if you get a critical point from the f prime being undefined. That happens when you have a cusp, because like if you have a cusp, like something like this flies in the face of the second derivative test, because this minimum is concave down on both the left and the right. But we are suggesting that if it's a minimum, it's concave up on the left and the right. And that's because this comes from the derivative being undefined. It has to be from it being equal to 0, not when it's undefined. Or let's say that it is defined, its first derivative is equal to 0, but the second derivative, when you plug the number in, you get 0 for an answer. In other words, it's not positive or negative. If that happens, the second derivative test doesn't work, it's inconclusive. So let's check out an example and try to make some sense of this. Use a second derivative test to locate and classify all x values of relative extrema. So we're not concerned about inflection points, we're concerned about extrema. Well, according to the second derivative test, I'm just going to copy this down. We need one of these two scenarios. That was a mistake. There we go. We need a critical value, that's what this is saying, when f prime is 0. So let's do that first. You don't need to write this down, by the way. I'm just pointing it out. You do need to write this part down. You find critical values from the first derivative by taking the first derivative and setting it equal to 0. Because by setting it equal to 0, we're saying here that f prime of x would be equal to 0. If I factor a 4x squared out of this derivative, I get this scenario. And then that is going to make x equal to 0 and x equal to 3. By the factor theorem, if you set each of these equal to 0 and solve it, you're going to get these. There is no situation where f prime here is going to be undefined. Even if it was undefined in some situation here, we don't care, because the second derivative test only cares about when f prime is equal to 0. Then, to continue the second derivative test, we need to find the second derivative. F double prime. That's going to be 12x squared minus 24x. I'm just using the power rule. I want to factor this still because it makes my life easier when I factor. So we need to take these critical values that we got from the first derivative, that's x is 0 and x is 3, and we need to plug them into this to see whether the answer is positive or negative. We are focusing on the second part right here. Plug the critical value that you got into f double prime, look and see if it's positive or negative. So if we put 0 into this, that's 12 times 0 minus 0 minus 2. That's 0. Now that stinks. That means the second derivative test is inconclusive. Bummer. Well, let's try putting the 3 in. That's the critical value that we got right here. That's going to be 12 times 3 times 3 minus 2. We only care if it's positive or negative. Positive, positive, you multiply two positives together, this is going to be greater than 0. Now here's what that tells us. According to the second derivative test, if f double prime is bigger than 0, then there's a relative minimum. I like to put an intermediate step into this to remind myself. If the second derivative is positive, then I always write concave up, which then leads me to x equals 3 is a relative minimum. And I should say which function is the relative minimum of function f of x. So it's great that we know that. What's not great is this being inconclusive. So unfortunately, the direction said find all x values are the relative extrema. We weren't able to use the second derivative test effectively to figure out what that was at the critical value of 0. So because that failed, we have to do a first derivative sign diagram. And we have to include on this first derivative sign diagram all the critical values from the first derivative. If we pick a test point in each interval, let's say that we pick -1, +1, let's say 10, even though this over here doesn't actually matter. We'll get to that in a second. If I put a -1, whoops, if I put a -1 into the first derivative, which is this, let me copy this down. This is what we're plugging it into. This is always positive, no matter what I plug into it, because if you square something, it's positive. So in each of these situations, the first thing is positive. If I put a negative in here, -1 minus 3 is a negative. A positive times a negative is a negative. So everything in this interval is negative. If I put a 1 in here, 1 minus 3 is also negative. Positive times a negative is a negative. So that tells us that this graph is decreasing and decreasing again, which means this is not a relative extreme value. It is neither. We don't have to write the decreasing there, by the way. So, in conclusion, second derivative tells us that x equals 3 is a relative minimum of f of x, and x equals 0, although it could have been a max or a min, it was actually not. Let's do another example of the second derivative test. Use the second derivative test to locate and classify all x values of relative extrema for each function. See if we have better luck this time. We need to find critical values of the first derivative. To do that, we take the derivative of f of theta. Derivative of 2 cosine of theta is -2 sine of theta. Derivative of minus theta is -1. We then got to figure out when is f of theta equal to 0. When is f of theta undefined? Although it being undefined is not valuable in the second derivative test. This is never undefined because there's no fraction here. So if we set -2 sine of theta minus 1 equal to 0, and we try to solve this, we are going to get a chance to review pre-calculus, which is great. Pre-calculus was the best. So sine of theta is -1/2. Well, what's theta going to be? Let me tell you what it is, and then I'll explain why. Theta, keep in mind, this says this on the interval from 0 to 2 pi only. Theta is going to end up being 7 pi over 6 and 11 pi over 6. That is without a calculator. So let's review. This would be side work if you need it, and I assume minimally for your notes you need it. When I write sine of theta is -1/2, I want the negative on top. And the reason is I remember that sine in a coordinate plane is y over r. I also remember that r is always positive. Y could be positive or negative, so I'm going to put the negative on top, saying that y is negative. Now, if you got the unit circle memorized, you're probably done with this problem and you don't need to pay attention. I prefer not to use the unit circle. I prefer to draw my triangle in a coordinate plane and make the smallest side in the triangle 1 and make the radius end up being whatever it ends up being. Since y is -1, we're going to be in quadrants 3 and 4. So I'm going to draw a reference triangle in quadrant 3, I'm going to draw a reference triangle in quadrant 4. And those should be the same size, by the way. Mine didn't end up the same size. Doesn't matter. Picture's not drawn to scale, but if they were, they'd be the same size. We're saying in each case, y is -1, and the radius is 2. Now, if you recognize this is a special right triangle, short leg is 2, long leg is the short leg, I think I said 2. Short leg in this case is 1. Opposite the long leg is going to be the short leg times the square root of 3. We went left, so it's negative square root of 3. Same thing over here. Opposite the short leg is 1. Opposite the long leg is that times the square root of 3. We went to the right, so it's positive. And the hypotenuse is always twice the size of the short leg. It's a 30, 60, 90 triangle. You need to recognize when that happens, and it's going to happen a lot. Since we use radians, 30 is 1/6 of 180. Using radians, that's 1/6 of pi, so that means the reference angle was pi over 6. If you're a unit circle purist, you might have written this a little differently. I myself am not a purist. You might have wrote y is -1/2, and this is 1, and this is square root of 3 over 2. And over here, similarly, we got -1/2, 1, and negative square root of 3 over 2. Doesn't matter to me. My brain works better with this. So, how do I have pi over 6 written in here, but I'm telling you this is the answer? Because the answer is the angle in standard position. So if I start here and go to here, the angle I have from here to here is 6 pi over 6. This is one more, that's 7 pi over 6. If I go from here, hold on, let me move this. If I go from here all the way over to here, well, that is pi over 6 short of 12 pi over 6, which is 11 pi over 6. All right, so that ends the pre-calculus review. There's no equation that we could write for this part right here. So the second derivative test, in a nutshell, make sure we don't lose focus of what's happening. We're going to plug the critical values from the first derivative when f prime was equal to 0 into the second derivative. If it's positive, it's concave up, minimum. If it's negative, it's concave down, maximum. So the second derivative, we haven't found yet. It's going to be -2 cosine of theta. Derivative of -1 is 0. So we got to plug in 7 pi over 6 into this. And we got to plug in 11 pi over 6 into this. It's going to be -2 times cosine of 7 pi over 6 and -2 times cosine of 11 pi over 6. Looking at our picture, 7 pi over 6 is this triangle right here. Cosine is x over r, so that's going to be negative. So this is a negative times a negative, which is going to give us a positive. Therefore, this is bigger than 0. This bottom one is going to be less than 0 because 11 pi over 6 is over here. Cosine is x over r, that's a positive over a positive, so we have a negative times a positive, which is a negative. If the second derivative is bigger than 0, that means that f of x is concave up. I don't think I specified on the last one. I didn't. I don't just want to say concave up generically. I want to say f of x. Is this function f? Yeah. F of x is concave up. Because if I'm not careful, someone could read this and think that I'm saying f prime is concave up or f double prime, but it's f of x. F of x is concave up. Therefore, there is a minimum at theta equals 7 pi over 6. And once again, I'm writing way too big. We have to say on which graph. Is this f? Is it f prime? Is it f double prime? And this is on f of theta, the original function. And since f double prime was less than 0 here, we would say that f of x, I'm sorry, I wrote x, these are thetas. I'm just chock full of mistakes. Poor child, hope you have an eraser. Now let's just get crazy. Let's just make this easier. F is concave down. Therefore, there is a maximum. You know what? Boy, I'm being lazy. Sorry. We should really be saying relative maximum, relative minimum. At theta equals 11 pi over 6 on function f of theta. So the second derivative test is valuable. You will find it to be more valuable when they give you certain pieces of information in which a sign diagram would not even be possible. That concludes the second derivative notes. Hopefully it made some sense to you. If it didn't, please let me know and I'll be glad to help you out.